Hello everyone. Just wait for others to join in, then we can start.
Hello.
Hi Rohi. Give me 2 minutes, Rohi. I'll just prepare the environment somehow and then we will start.
Sure.
You might be expecting a couple of new faces from this session. So let's just wait for 1 minute and then we can give it a start. Or maybe we can start and then others can join in if they're joining in. So let me then give it a start. So uh, let me share my screen, share our notes. Okay. I hope you can see it, Rohi, now.
Yes.
Okay. Okay. So we had a bit of gap. So let's just quickly revise what we were saying with respect to the logistic regression modeling. So we started off with the classification use cases, and we understood that if I have use cases where I have x-axis and y-axis, where x is my independent variable and y is my dependent variable, and I have data set which is distributed in a format as if it looks something like this. So there are certain cases which is uh, falling in one grade as opposed to other cases which are falling in another class. Whereby we can say that we have a multi-class classification problem. In this case, we can also call it a binary classification problem. Then fitting a straight line through this is not going to solve my problem because there is this portion and this portion which is not explaining my model very well. And then if I take the distance, right, uh, from my regression line from each and every of these points, and that's how I calculate, right, the the sum of squared errors. So if I take the distance, if I can somehow take the distance, maybe this line that I have drawn is not really good. Let me just redraw the line. So maybe in this case, my linear regression line would look something like this. And then my so-called residuals or my errors will be the projections of individual points on this line, right? Now, in this case, the problem is that, as we can clearly see, we have a big issue, and the problem is as simple as uh, we have a very big distance from the line to the actual points, and hence my accuracy will never be good, and hence I have to fit something else. So that's the reason why. That is the exact reason why we chose not to go ahead with linear regression, but with something that looks like this, right? And this curve that we were talking about is otherwise known as a sigmoid function. This is a sigmoid curve. This is a sigmoid function. And using this sigmoid function, what we are essentially doing is we are trying to fit a probabilistic model. right? We're trying to fit a probabilistic model where we're trying to go as much close as possible to the points on the top as well as to the points at the bottom. But there will be cases where there will be misclassifications. So to cater that kind of situation, what we are saying, I'm going to call a decision boundary. And whatsoever is falling on one side of the decision boundary, let's say if my points are on this side of the decision boundary, I call that a 0. If my points are falling on this side of the decision boundary, I call that a 1, right? Or the ones which is on this side, on the right side of the line, I'm going to call them the 0 points or the O points. And the ones which are falling on the left side or beneath my prediction line or my fit is also going to be known as my X points, right? So this is the reason, or this is the way how I am actually defining it. And then I see that being a very simplistic model, I can represent this very well if I understand what is a sigmoid function. So that's where the entire story started from, where we simply took the equation of a linear regression line, which is y equal to some weight multiplied by or multiplied to my features or my dependent variables added with a bias. So this B term over here is my intercept or my bias, and the W term over here is my slope or my weight. Now, if I have a hypothesis in this case, which is to represent my situation in form of a sigmoid function, then clearly my sigmoid function is a sigmoid of y, where the hypothesis is on x, because x is my dependent variable and I'm trying to predict y. If I expand the sigmoid function over here, then it comes out to be something like this. So mathematically, sigmoid of any value t is equal to 1 divided by, okay, 1 divided by 1 plus e to the power minus t, right? And the reason why we are doing this is because this is a logarithmic representation, okay, of this range, of this line. This line is represented by this kind of logarithmic expression. And why we are doing this is because a natural logarithm, if I talk about, it always converts the limits of any number within 0 and 1. So if I take a natural logarithm of a very, very big number, which is close towards positive infinity, then the value converges towards 1. If I take a logarithmic or a natural logarithm of any number which is very, very small, minus infinity, then this value will converge towards 0. So I am able to simply put bracketize, or let's say containerize my data within these two ranges. And that's exactly what I want here, right? Because I have two classes of data. I have some class which I can call 1 and another class which I'm calling as a 0, right? And using this log function, I'm able to do this very, very easily, right? So that's what is the essence. That's what is the basics. That's what is the ideology. Now we are going to look at how or what kind of, it's a mathematics is involved into this, or what kind of things are involved inside this, right? And then we can try to see what is exactly going on over here, right? So what I am going to do is that I'm simply going to go through the mathematics first, because a bit of math is really required. I'll tell you why this bit of math is really required is because the math is required only in cases we are not able to deliver or we are not in a position to use ready-made libraries. There will be many such, let's say, situations which we will face in our uh, implementation career, or our in the phase of time when we are trying to implement things, right? We will face organizational or operational challenges, or let's say restrictions, in other words, where we may or may not be in a position to really implement things using out of the box solutions like, let's say, scikit-learn. So obviously, in our case, the library that we are going to use, so the most prominent library to implement the logistic regression, right, for us would be sklearn or scikit-learn, right? Obviously, we are going to use this because it's a production ready system, but then there are cases, and I am also personally aware of those cases, whereby organizations or the setups in which we are working, they'll not really rely on anything which is open source because of variety of reasons. The security of data being one of the major concerns, right? Because to ascertain whether or not this scikit-learn implementation of logistic regression is not doing anything nasty with my data, or it is not taking my data away from me, or it is not allowing hackers to uh, come inside my system, or in other words, it is not making my system or my infrastructure vulnerable. I have to ensure that I'm using implementations that, first of all, I can control, and the second thing, that I can end-to-end understand, right? How this helps is because it also gives you the control on how you're going to write the algorithm. Now, that's the region, or that's the place where, or that is the only place where you will see organizations and our friends working in those organizations using programming languages like C, C++ to do the implementations. In some cases, softwares like SAS is also used. But I'm not sure if I've heard about the software called SAS, but it's a statistical modeling tool similar to R. We have not really covered R as part of the sessions that we are doing over here, but then R is a very, very prominent statistical tool, and so is SAS. And the reason why it's a prominent statistical tool is as simple as because we uh, can only expect, or we can only expand the horizon within the software's lifecycle itself. So what I mean by that is, if I'm doing a sklearn kind of an implementation, the data can be practically anything, because I can read any kind of data using pandas, right? I've seen, or at least as of this point in time, we have read only textual data. Later on, we can even read, let's say, JSON data, we can read XML data, we can read images and videos as well. So that is the power which we have in the libraries which are surrounding sklearn. So using NumPy, I can do all the mathematics. Using pandas, I can actually literally read and import any kind of file. And there are other Python libraries as well, by means of which I can really process any kind of file. But then what is the reason, or why did I say that SAS makes a statement of exclusivity? Is because if I'm doing a model and by some means that model comes to you, then you will be able to out of the box implement or use that model without any investment other than the Anaconda software that I'm using, right? The only software that I'm using over here is, let's say in this case, Anaconda, right? So Anaconda Python distribution is something I've installed. And if I'm creating a model, there are even libraries. One of the libraries is called PICKLE, Pickle, by means of which I can save my model and export it. So somehow, let's say you get a hold of that model, and all you need is any Python implementation on your side. You don't even need that exact version which I'm using, and you should be able to export and reuse your or the model that I have created, which for some organizations, basis the kind of criticality of the data, is a challenge, is a concern with respect to security. That's why softwares like SAS is also really very prominent in the market, where the data or the models which is created in one SAS platform, in one version of that software, can only be read in that version or any compatible version of that software or the version. And the data that is read via SAS, or the model which is generated by SAS, becomes exclusive only to be read and executed by SAS. The other places where we use other programming languages, let's say the examples which I was taking, like C, C++, is going to be cases where organizations would like to, from scratch implement all the algorithms that they're going to make use of. So this is quite prominent in case of FIIs. So any financial institutes are going to do so. Hardly or majorly you will not see that scikit-learn based models are going into production. In those cases, they will be writing the algorithms from scratch using that. So that is the reason why we need to know what is the algorithm behind it, and how these algorithms really help us in doing our job, right? So I'll take a quick pause here. Maybe if there are any questions, you can let me know. If not, we can progress. So I see one question. Give me 1 minute. Okay. And you also type me the source here, Rohi, from where you have checked this.
Yeah, just Googled and saw the graph of log.
Okay, let me just do that from my side. Yes, yes, true. So what you are saying is correct. Yes. So yes, so this is true, but the implementation that we have over here, right? It is taking the logarithm form here. So because we are doing a division, then this logarithmic expression is going to convert in this format, right? So maybe this is not written in the right way. So maybe I can say that this is something like this: the sigmoid uh, representation. Okay, so I'll just put a bracket. I'll put a bracket of sigmoid representation of this logarithm is going to be something like this, right? Because what we are doing in the natural log is essentially this much part that we are doing, right? So the calculations are at the bottom. So as it increases, we are going to control that in that way, right? So let's say I'm just trying out in a calculator. Let me just see if my understanding is right or not. So if I take a very small value, it is so small that it calls the result as not a number because it is very small. If I'm taking a very large value, then it is giving me a number which is into decimals. And then if I do 1 divided, where is the calculator? 1 divided by that number that I have got, then it comes to be a bit closer to 1, right? So you can try this out. If you take a natural log of, let's say, 1 lakh, okay, maybe how much have I taken? 1, 2, 3, 4, 5, right? So in another window, I'm doing the calculation. You can do that from your side. If you take a natural log of, let's say, 10 lakh, it comes out approximately 13.81. You divide that from 1, you get this, right? So you get a value which is something like 0.08, right? And it is moving closer to 1, right? So the implementation is here. It is not the entire function itself, but the natural log helps you to keep the range, right? So it may not be a direct impact like the one which I wrote earlier. I believe that was wrong. So if I put this into a sigmoid form, that's how it is going to be.
Okay, yeah, got it.
Okay. But let me also search for a use case. Yeah. Yes. Got yes. Right. Okay. So just a few things before we really start. So the first thing I wanted to clarify is that graph, right? So that the sigmoid function or the curvature, I'll write, is also called a logistic function. This is something maybe we discussed in the last uh, class, but I just wanted to keep this in mind. It's called a sigmoid curve, it's called an S curve, it's also called a logistic function because ultimately this is going to be the representation in which I'm going to use that. So that's just an interchangeable name, but you need to remember that the reason why, depending on the library or the function or the custom algorithm, if we want to, the way we are writing it, the name is going to change. So if we are taking any reference, then we have to be aware of the naming convention. And then this base E, right? The exponent, okay, the exponent function, I can say the exp function which is there in the denominator, okay, is measured by, is governed, I can say, governed by the value or uh, calculation of the letter E, right, which is this one. Let me just take a tab. This is also known as the base of the natural logs, right? This is the mathematics. This is just a basic of the mathematics which is behind this. And now we can try and see how we can essentially represent the mathematics in a different way so that we are able to understand how the implementation is going to be. Because if we know how the implementation is going to be tomorrow, if we have to implement it ourselves, right, then we can do that. then we should be able to do that quite easily, right? So the first thing that we need to uh, understand here is that the basic difference now comes with the decision surface that we are creating, right? So we are no longer going to be concerned about any iterative algorithms or any iterative processes, in this case just like gradient descent, right? So gradient descent was something which was there when we looked into, let's say, machine learning, right? So when we were looking into linear regression, we were looking into uh, the concept of gradient descent, where we were descending to find out uh, the most uh, good values, okay, the really good values, okay, the real good values that we have for the weight, so that we can minimize the cost function, right? But here there is no such concept, because we are not plotting a straight line, and we're not going to change the straight line from one place to another place, okay? So logistic regression equation, how that equation is actually put forward. So let's just try to write it over here. And if we write the equation, or let's say the formula or the equation of logistic regression, okay, is given as, just write it over here, y. So y is my outcome. This outcome is given as e. Okay, I'm representing that exponential function or the base of the natural logs as e, right? So that's what we are going to use. So e to the power, I'm going to write to the power like this, e to the power something, and then we are going to divide that with 1 plus, okay, 1 plus e to the power, okay, something, right? So this is how we actually mathematically represent it, or when we are going to write the implementations, right? This is how we are going to write. So this is fundamentally different from this one. Why is this so? Is because this is the normal or the regular equation of a sigmoid function. Now the sigmoid function is the underlying, you can say, concept or the baseline, the skeleton on which uh, logistic regression is going to work. But how, when it actually works, it uses a function, it uses a formula, which is something like this, right? And then we are going to define what is going to be inside this. Now, clearly, logistic regression is something which we have borrowed from the linear regression concept. Let's make our life easy. Let's say that we have only one independent variable, which is x, right? So I'm just going to make my assumptions clear. So where e I have already defined. So I'm just going to write e is the exp function or the ESP representation, and let's say x, okay, x is our independent variable. So x is my independent variable and e is my exponential representation. Now in the above equation, I have not even put down x, but before I put down x, let me just clarify it in a different way, that if I had linear regression equation, then it should have come up like this. So in this case, I need x, and then I need beta 0 and beta b0 and b1, or theta 0 and theta 1, right? So I'm going to represent them as t0. Okay, t0 is theta 1, it has 0, sorry. So t0 aka theta 0 is my intercept, and theta 0 is equal to intercept or the bias, and t1, I'm going to represent this as theta 1. So t1 is just another name I'm giving to theta 1. Theta 1 is my slope, okay, slope or my weights, right? So now how do I combine x along with t0 and t1 so that I get an equation which represents the linear regression format, right? So to do that, and if I'm able to do that, I can simply put it over here. I can simply put it in these brackets and my job is done, because I'm simply taking that straight line, which was a linear regression fit line, and I'm trying to convert that into a logistic regression using the concept, okay, using the concept of a sigmoid. So I'm just using the sigmoid as the skeleton, and I'm trying to convert it into a function which is something like this. So clearly, linear regression is what? Linear regression is as simple as y is equal to if I have theta 0, then it should be theta 0 plus theta 1 x, right? Or I will say theta 1 multiplied by x. If I have a simple linear regression. So I'll just take this part, which is my right hand side, and I'm going to impute it over here, right? So there will be multi-million ways in which you can implement this when you are trying to do the programming part of it. So you can calculate these parts, let's say separately, and then you can feed it into this formula using functions. So you may have one function to calculate this much part, and then you can simply put it inside this, inside the exponent, right? Now that's one way of doing it. The other way uh, of doing it is going to become complex when you have more than one let's say independent variable. So if you have more than one independent variable, then this equation becomes very, very lengthy, and then it really becomes a tough thing for you to find out theta 0 and theta 1, because then we are back to square one. We have to do linear regression first, we have to do the gradient descent first, and then once we are done with that iterative process of, let's say, gradient descent to find the proper values of theta 0 and theta 1, then only we can get back here and we can try to impute that value, right? Because to find theta 0 and theta 1, if I represent this equation with respect to theta 0 theta 1 kind of things, right, then obviously I have to run a gradient descent, which I'm trying to avoid, because if I do that, then what is the purpose of creating a probabilistic model? Because then I will be confused with respect to the boundary, the decision surface that I'm trying to create, because then I have to define one equation for the line, which is the curvature, and then one more equation has to be defined for uh, the decision surface itself. So why not make our life simple, and why not try to represent this in a different way? So if we represent, or if we try to represent this in a different way, right, then the easiest way to do that is to use the basic concepts of probability, which we have already seen earlier. So we're just going to reuse that, and then we are going to represent logistic regression in that format. Now, that is not to say this formula or this equation is not going to work, right? In other words, we can say one common way of representation for one or a single independent variable. Okay, this formula will still work, right? One common, let's say, representation. I'm just going to get rid of this two words way of. So in case you have a single independent variable, you have a considerably small, let's say, data set, 100, few hundred MBs, maybe even up to a GB, then you can simply go back to what we have already learned, and you can try to find out the values of theta 0, theta 1 using the code, the functions that you're going to write. And then you can apply, let's say, gradient descent, and then you need to know how to implement the gradient descent also, because we have only seen it in a conceptual way. We have not looked into the derivations, right? We have only looked into the final formula which we got out of the derivation, but we have not looked into how to actually solve the partial derivative. Now, and then after that kind of a complexity, you can arrive onto this, which is doable. I'm not saying that it is or it cannot be done, but then because my final outcome is 0 or 1, it's clear that I have a probabilistic model, and it will be better to model my outcome in a probabilistic method. So that's why one quick and one easy and one very practically implementable way is to reuse the concepts of uh, probability related things that we have learned. So what we are going to do in that case is that, let's try to take an example. Let's say if we are trying to model, or we are trying to find out whether a person, using a logistic regression model, we are trying to find out whether a person can be classified as a male or female, let's say, right? It's a very simple and very idiotic kind of an example. I'm having some kind of a data, and I would like to predict whether a certain observation belongs to a male or it represents a female, right? So how do I do that? Is that I'm simply trying to, I'm simply trying to find, find the probability, or maybe I'm going to write it in different way. One better mathematical way is, find the probability of okay, occurrence of one outcome as opposed to another. Okay, what is the assumption? In this case, the assumption is clear. If I have an observation or a row of data which represents a male, it can never be female. So the events, right, the events or the outcomes are independent events, right? So if one occurs, the other cannot occur at the same time. If that's the case, we can simplify our life in this way. So if we write that, if we try to write, let's say, example given, if we are trying to model our outcomes, that an input X, right, belongs to the class or the output class Y is equal to 1, okay, then, right, then I can write this in the probability format as, or my formula is going to become the probability of getting an X is equal to the probability of getting a Y equal to 1, Y equal to 1 given X, right? So the probability of finding the outcome of X, or the probability of finding to which class this input X belongs to, is simply represented in a format like this, right? It is simply represented in a format like this. Now, later on, when we look at conditional probability, you might get confused with this pipe sign. We will be looking into other algorithms like naive Bayes, which is also a classification algorithm, where we will be extensively using the naive Bayes principles or the Bayesian probability, where there is a concept of conditional probability. Now, conditional probability is something which we have very, very briefly touched when we did the basics. We did not do it more because we wouldn't understand without a real use case. That's why we skipped it there, but we have to do it later on. So when we do that, we will come across this sign more, right? But in case of the difference in this representation and the conditional probability representation is that there is no interpretation in case of a conditional probability. In other words, that equal to 1 sign that I've highlighted will not be there in the conditional probability world, right? In the conditional probability world, maybe we would like to focus on the probability of getting rain or having a rain, provided I'm wearing a blue color shirt, right? So that's the representation in case of a conditional probability. I just wanted to quickly touch base on that, because later on we should not be confused as to why we are representing it like this, because this looks similar to the conditional probability. It looks similar in the way that I have actually written it over here, but it's not the same. It's a completely different thing because I'm already giving y a value, right? I already know what is going to be the value of y because this x belongs to my training data, and I'm already aware from the training data that it belongs to a class y equal to 1. Hence, the probability of what is going to be the outcome, right? The probability of what is going to be the outcome can be represented like this. Now, if you would like to simplify this for your understanding, you can clearly say y equal to 1. This terminology can be replaced with 1 because we know that y is equal to 1, right? And this will not be read as given x. So y is equal to 1 for every x. So for this x which I have, which is an input, I already know that the outcome is going to be 1. Hence, I am simply representing it like this, right? Now, the question comes, why are we trying to predict the probabilities? We're trying to predict the probabilities because end of the day, our logistic implementation, right? Our logistic implementation is uh, it's a advising us, or it is restricting us within the range of 0 to 1, because that's the kind of use cases we are trying to solve using logistic regression. So we are trying to bind ourselves within the range of 0 to 1. So again, we are back to that same concept that whether our mathematical output is helping us resolve the problem by limiting us within the range of 0 to 1. And if there is any technique by means of which we can do that, then that specific mathematical technique is going to work, right? So if I do a derivation using this concept, using the natural logarithm concept of this part which I have over here, then I can clearly represent mathematically, if we derive to a probabilistic representation of our earlier function, we will get, okay, we will get an outcome which is this theta 0 plus theta 1 multiplied by x, right? This terminology can now be represented as natural log of something, and that something is the probability of x divided by 1 minus the probability of x, right? So now I hope you have got the concept. What we are trying to do is that we are representing the exponential function or the exp function represented by this e value, which is taking a power of my regression equation, where I consider the regression to be a simple linear regression or a single value regression. And from there, what I'm trying to derive is that if I formulate this in form of a natural logarithm, right, then my denominator is going to cancel itself out. And hence I can say that my equation can now be represented as a logarithmic expression, right? Now, if I have a logarithmic expression, I can now use this, right? I can now use this part, which is on the right hand side, and there is a specific name to this as well. I can use that specific thing to find out the probability of one event happening if the other one is not happening, because the events are independent. This concept is known as the odds of the default class. So I'm going to take this and I'm going to put it over here. The RHS of the above equation, which is this, is also called the odds of the default class, right? Now, why is it called the odds is because you can clearly see that whatever is inside the natural logarithm part, why is because inside the natural logarithm function, we are using a value which is something like this, right? And this value, where this value helps to get the chance of one event occurring if the other one does not occur, right? So it nullifies the effect of one of the events happening to find out how the other event is happening, right? So that's the most easy way in which I can represent the equation in a probabilistic sense, because now it has become easy for me. Now the problem here is, if I'm going to represent it like this, did I really solve the original question which I was asking? The original question which I was asking is, I know, I understand I have to represent my output in a binary format, right? But then again, we still have that basic problem. The basic problem still remains. What happens if I have more than one independent variable? If I have more than one independent variable, am I going to calculate the probabilities for each and every independent variable or a set of those variables, right? So for multiple such cases, right, for multiple of such cases, we have to do that. We have to calculate that. But now, rather than doing the calculation in an iterative way, which was the earlier stance, where we were trying to do some kind of gradient descent to find the values of theta 0, theta 1, now I have a probabilistic representation. And if I have a probabilistic representation, then my calculation is quite simple, because I know the outcome is always going to be in the range of 0 to 1, right? In other words, in a simplified word, I can say that for every probability of every event, any one event out of two, we have only two events, right? So in our example also, we are saying we are modeling the data to find if the data or the observation belongs to, or it represents a male or a female, right? So I have only two possible outcomes. So if that is the case, then for every probability of any one event, right, there will be an inverse probability as well, right? So that is for each p of x, we have a similar probability 1 minus p of x, right? Now what we are essentially doing is we are simply taking the natural log on both sides. Both sides of the equation can be taken as natural log, and because I took a natural log of this equation, it got a representation of this. So if I try to derive this by taking a natural log on both sides, I will be coming over to this. Keeping in mind, I have a simple probability representation of x and y in this format because my input x belongs to the output class y equal to 1, which is represented as this. Now, if I take a natural logarithm on both sides, then y becomes this, and my right hand side is this. So I take a natural log on both sides. The exponential function is gone. Okay, this part becomes null and void. My exponent and the logarithm is going to cancel themselves out. And what is left out is this much more. So that's why my left hand side becomes theta 0 plus theta 1 multiplied by x. And my right hand side, which is my probabilities or the probabilistic representation, becomes a logarithm of the probability of the outcome of x divided by the probability of what is not x. And because this is represented as a ratio, it is also known as the odds of the default class, or it is odds of the class, right? So I can simply say odds of the default class x, or default class x when y is equal to 1, right? Now that I have written it in this way, will I be able to represent multiple variables? Will I be able to represent multiple variables is the question. Do you think this can be represented as multiple variable if there is any way to do this? If I have, let's say, multiple x's, can we represent that in this case? Any idea?
Yeah, I'm thinking, but I'm not able to get it.
Okay. So the fact of the matter is, I am able to represent the logarithm. So what happens? Let's say I'm going to write it like this. What happens in case we have multiple independent variables? In case of multiple independent variables, what is really going to happen is I can take the logarithm, right, of the probability that I'm trying to find. So what is that? So sorry, I should have written it like ln. So I'm taking an ln of this, right? I'm simply going to paste it over here. Now this x is what? Y is equal to 1. X can be represented as y is equal to 1. So I'm trying to represent this value in form of a mathematical expression, or a mathematical expression that I'm trying to find out, right, is going to contain multiple variables. Can that be represented like this? The answer is yes. Why? Because if you have an equation, if you had an earlier equation which is something like this, and this part simply belongs to the linear regression formulation, then irrespective of what is here, you can still apply the natural logarithm on both sides of the equation, and you will be able to extract this part out, which means if for any use case I have multiple independent variables and I represent my logarithm like this, or in other words, I can represent it like this also. Can I say this? Because 1 minus p of y equal to 1 is nothing but p of y equal to 0. Right? If for any observation, the outcome is 1, let's say 1 represents male, then 0 represents a female, then y equal to 1 represents a male, then y equal to 0 is going to represent a female. So 1 minus p of y equal to 1 is the probability of getting a female, which I can represent it as probability of y equal to 0. So these both terms are the same. So interchangeably I can use them, and I can say that this is equal to, if I take a natural logarithm on both sides, and we can simply consider that in this bracket inside this equation, if I have a multiple linear regression formulation, then I can simply write it like this. I can simply write it as theta 0 plus theta 1 x1 plus theta 2 x2 plus theta 3 x3 plus until theta n xn, right? So now that we have represented it in this format, we no longer need to calculate this. So that's the advantage we are getting over here. If you know why I did why I took the logarithmic approach, or why I took the probability approach and then merged it with the logarithm on both sides. The reason why I did that is because I wanted to exclude or expel the dependency of calculating a gradient descent, so that I can arrive at the values of theta 0, theta 1, which I don't need anymore. I don't need anymore because I can simply ignore the weights and I can calculate this. If I'm able to calculate this for each and every feature, for each and every independent variable, then I will anyways be resulting into this function in a sigmoid way. So if I take a logarithm of that, then I get the equation or the representation which was the same as the linear regression use case. So in other words, I'm simply trying to represent this thing over here as equal to this equation over here, right? If I am doing this, then irrespective of how many thetas are there or how many x's are there, I will still get the output quite easily, although I just have to calculate the probabilities for each and every x, right? If I have independent variables like x1, x2 until xn, for each and every one of them, so x1, x2, xn, just to clarify, where x is actually a set, is a set of x1, x2, x3 until x of n, right? So x is basically a set or an array or a vector, right? A single row vector of all the values of all the independent variables represented as x. And then I can try to find the probability of x equal to one value and try to find the probability of x which is not equal to that value or the reverse value. And this concept I represent as the odds of the default class. If I'm able to calculate that and take a natural log, I'm also able to represent that as this formula. Or in the other words, I can represent this formula as a natural log of getting a probability of one of my desired outcomes by the probability of the other outcome. And hence I'm able to represent it like this. Right? So this is one way to understand, or this is one way to understand how internally my logistic regression is going to work. Right? Now, when I really do this, what I'm going to do, right? What I'm exactly going to do is that, or let's say I'm going to write this as the algorithmic procedure. or the algorithm itself, right? So the algorithm to calculate this will be, first of all, I have to get the weights, right? Somehow I have to get the weights. If I don't get the weights, okay, give me 1 minute. Sorry for that, I got a call. Um, I have to get the weights. Somehow I have to calculate the weights. So I have to calculate the weights of each and every feature which I have. Now, how am I going to do that is something which we are going to look at when I do the practicals, because I have to take some kind of a data to explain how I'm going to calculate the weights. But I have to get the theta 0, theta 1s. Because if I don't get the theta 0, theta 1s, then this equation or the representation is really not really possible. I have to convert this. Finally, I have to converge this part into this part, right? So now I have to get the weights. So let's say somehow I have got the weights. If I get the weights, then I can get the log ratio as well. So the first thing is I have to get the weights. The second point is, or the second step is, I get the log of odds, or I get the odds and I take the log, right? And the third part is going to be to find out the standard error. Find the standard error, right? How we are going to find out the standard error is something which we are obviously going to look at when we implement it, but the standard error is not to be confused with the standard deviation. Standard deviation is different, standard error is different. Why I'm calling standard error in this case is because in statistics, a standard deviation or a concept of a standard deviation applies to a population, right? So a population mean is represented by X bar and the standard deviation is represented by sigma. When we talk about a sample, because we are never going to work with the population, right? We are going to work with the samples. So if I'm going to work with the samples, then what I'm going to do? I'll have to consider the standard error, because the standard deviation becomes standard error after normalization when I'm going to consider a sample, right? If you are not clear about this concept, please do let me know. I can explain you how the standard error is really calculated. But the point here is, because we are working with a sample, I have to calculate the standard error because I need to know how much my model is really away from the actual reality. So what is the error which is there in the model? Because if I don't calculate the error in the model, how am I going to know how much well I have really predicted it? So example, if for some specific row or for some specific observation, the standard error is very high, right? Then I can't say that I have predicted that point really well, right? So if I've not predicted that point well, right, then I consider that as an error in the prediction. And there is a certain way in which I'm going to represent the errors as well. It's the same table which we have seen earlier, which is known as the confusion matrix. So I'm going to put all of these details into my confusion matrix, especially the calculations that I'm going to do using the standard error. And I'm going to create the confusion matrix where I see that, let's say out of 100, if I have 100 cases or if I have 100 rows, how many have I correctly populated or correctly assumed or correctly predicted, and how many I have wrongly predicted, right? So there will be 4 terms which we are going to use, and we are going to go in depth in there as well. Of course, we are going to, but the terminology that we are going to use in there is going to be standard error because we are playing with the sample of the data, right? So once we have calculated this, now our advantage is because we are going to use sklearn, this all will be calculated inside sklearn itself, right? So this all can be used inside sklearn itself. Inside sklearn only, it is going to estimate this, it's going to make the calculations, it's going to give us all these values, depending on the implementation of the API. Maybe it's not going to tell us the weights. It may or may not always tell us the log of odds, but it's going to tell us, or it's going to return us the standard error of the model always. And basis the standard error of the model, we can come to know how good or how bad for each and every prediction our model is. So now the basic concepts of how we used to, right? How we used to get, or how we used to understand the probability, or how we used to understand the validity of a model changes. Because what we have seen earlier in case of a linear regression line is we used to calculate the total error, right, by calculating the sum of squares of all the residuals. That's exactly what we have done in case of a linear regression problem. But in case of a classification problem, this entire concept is changing, because now I'm only concentrating on one kind of error. It is not a summed up error. So the standard error that I'm talking about is an individualistic error. The standard error, the STDERR, is otherwise an individualistic error. Okay, in the sense that it is calculated for each and every observation, but it is not summed up for the entire model. It is not going to be summed up for the entire model like we did in case of linear regression. We found out the sum of squared error, or the total error. We're not going to sum it up over here. Why is that the case? Because for each and every observation, we have to predict either 0 or 1. And how we can find out, or how we can be sure that our prediction of 0 to 1 is accurate, is by looking at the standard error of that specific row. So example, there is row number 10 in my data, and for that the standard error is very high. Clearly, the prediction that I have made is wrong. Right? If the standard error is very high, the prediction is wrong. If the standard error is very less, it is correct. Right? Now there is a way to let's say formalize what is high and what is low. We are going to look at that. When we implement it using a data set, we'll come to know what is meant by low and high, because we already know these are things that we can't really say, okay, if it is greater than this is bad, and if it is less than that, and it is good. So that's not really the case, right? We have already seen that in case of linear regression. We calculated a lot of R square values for each and every model. Finally, we settled with one of the models where R squared is equal to 30. Or I think R square value was something like 0.71, and mean squared error was equal to 30, right? So we settled with the model of mean squared error is equal to 30, because that was the lowest out of the 7 models or the 10 models that we created. We can't say that a mean square error value of being equal to 30 is a very good model. So there is no such kind of it's a benchmark which you can use to say that, okay, the value of 30 is really good. If it is less than or equal to 30, go ahead. And now you can put the model into production, your client will be happy. So there is no such thing, no such thing at all. Right? So again, we have to try a lot of different observations, and then we come to the conclusion. Right? That's another concept of regression analysis that logistic regression uses. Logistic regression, being a probabilistic model, will never really tell you, right, that this is the exact identification of the value. Right? In other words, it's always going to give you a probability of how much likely the value belongs to one class as opposed to the other. Until this point, is it clear?
Yes.
Yeah. Okay. So, give me 1 minute. Yeah. Okay. So once we have the model, and we have, let's say, the hypothesis which is ready, then we can try to create the decision boundary. and then we can find out which values we are going to take on one side of the boundary and which values we are going to take on the other side of the boundary, right? So that is something that we have to decide ourselves. So that's one point that we have to remember always. We have to always be remembering this thing. We have to always remember this thing, that the value of the decision boundary, right, it cannot be calculated or it cannot be determined. So there is no book, there is no text which tells you, okay, you have to take a decision boundary of 0.5. No, nobody is really going to tell you that. So that's a very it's a difficult and complicated thing when it comes to uh, implementation of any such classification algorithms which uses a decision boundary. The concept of decision boundary is a bit simpler when we use somewhat advanced models, when we go into uh, models which represent my data in form of a binary tree or a tree-like shape. Then the concept of a decision boundary is going to change a little bit. Then maybe it's going to help us. But in this case, so I can write, in case of logistic regression, the decision surface or the value representing it is up to the researcher or the statistician. For one use case or setup, it would be 1, while it would uh, be another, or let's say different value for another setup, right? For example given, in any particular business scenario, a decision boundary of 0.5 is a good start, right? Example given, in case of medical use cases, right? If I have medical use cases, so use cases which is there in the healthcare industry, right? If I have that kind of use cases, 0.5 is no longer a good thing. Why? Because let's say I'm trying to predict whether I have cancer or not. 50% being the benchmark or the deciding value is really not good, right? It is really not good. I have to increase the probabilistic representation of the model. It has to be more accurate than that. So maybe in case of ethical use cases, maybe my decision boundary can be 0.9 or as high as 0.9, right? So that's the point. I mean, to decide the decision boundary is entirely up to the use case which we are trying to solve. It has really nothing to do. It has really nothing to do with the mathematics of the logistic regression. The mathematics of the logistic regression is a different thing, and what we are trying to predict will obviously be dependent on the decision surface, and the choice of the decision surface or the value that we choose is going to be completely different, right? Please keep this in mind. Please don't get confused that my model is going to give me the decision surface. In case of a logistic regression, it won't. There are other models where the output will not only contain details like the standard errors or the accuracy or the confusion matrix and so on. It's also going to tell you the decision matrix, right? There will be advanced models which can handle more and more complexity, where we will have that kind of a thing. But in this case, we are not going to have that. In this case, we are not going to have that, right? So let's take a logical close over here. We are going to continue tomorrow. I would strongly recommend you to read a couple of things. I'm just going to ping it here, and that's going to help you to understand the concept of what is a logit and how it is really represented. Please look for this on this website that I'm just pinging over here. So if you look for this, and if you check the implementation or the way this person has really represented it, is really good. The channel's name is StatQuest. It is there in YouTube. If you want to refer for a very simple mathematical intuition, if you have not understood the logarithmic form of things, because for the first time we don't understand that. It's quite understandable that we are not able to digest what is going on with the natural log taken on both sides and so on. How does that curve fit and all these things. So if you want a very simplistic and different kind of approach to understand how exactly logistic regression works, but from a very overall, a broad view, it's not a really very mathematical view, it's a broad view. So you can look at this video, or you can look at this channel where you will find a video, right? I think let's make a close over here. I'm going to stop sharing, Rohit. Let's continue from tomorrow.
Yeah. Yeah.
Okay.
Thank
Thank
you.
you so much.